So it's going to record this as a video, and you should be able to watch it. I've heard one of these, and I can watch it. I'm not sure if you can. Oh, one more thing, some good news is evidently the school's been blocking a lot of this stuff, and you're having to use your own home computing devices. My understanding is now they're going to remove these blocks. So I don't know if anybody has their student computer there, but maybe you could try it as well on your student computer on the side. And if you're having problems still, maybe you could do a screen capture and then email me those problems or somehow get it to me so I can forward those problems on, because it's not right that you guys got a computer and you can't even use it. Okay. Okay, so without further ado, what we're going to do is we're going to whiteboard the very last set of problems on the lab response. That's 24 through 27. What this is, we have an insulator in here, and it has a charge of positive Q. And then we're enclosing it in another spherical shell that's also an insulator, but this one has a net charge of 0. Okay, so what I would like you to do in this first part is I would like you to answer part A, part B, and then for part C, I just want you to figure out what the E field is for this insulator inside the middle part. That's why it says little r is less than big R. So inside of that. Okay. Any questions before I let you go? Okay, I'm going to mute you so that you guys can talk on your whiteboarding site, and give you about 5 minutes to do this. Okay. Oh, one last thing. When you're doing this one, please show your work. And since you can't do the integral symbol probably, maybe you're going to have to write it out with, the drawing tool or whatever. Kind of like, I know it's going to be sloppy, that's all right, but please show us Gauss's law what you're doing. Don't just jump right to the answer for part C, okay? All right, so now I'm going to mute you. Okay, I'm going to call you guys back. And Laura and Karina's group has volunteered to present their findings, so I'm going to switch it over to Karina. Okay, and so the first question I think was, how much charge is on the inner surface of the insulating spherical shell, I believe, right? And what did you guys say?
We said plus Q.
Plus Q. Now, let me ask you a question, first of all. Overall, it's neutral, right? Can charges move? Yeah, okay, can charges move on an insulator? Are they free to move?
No.
No, they're not. So, how would there be a positive Q on that insulator on the inner surface?
It says the total charge of the sphere is positive Q.
That's true. The inner one, it is, right. The inner insulator, it is. But I think let me take over. Yeah, the screen is kind of going a little bit crazy there, too. I might have to switch it over to Laura for a second. I'm going to reclaim the presenter role. But here, let's look at the question again. The question again says, how much charge, if any, is on the inner surface of the insulating shell? So in other words, here, let me draw what I'm talking about. And I will do it in blue. It wants to know how much charge is on this inner surface of this shell here. I agree with your group that the charge on the insulator in here, I agree that that charge is given as being a positive Q on this one, okay? But my question is, how much is on the inner shell here? And let me see if I can pass it to Laura, see if it it's funny. I think either one of you can actually talk, though.
Right.
Okay, so how much would be on the inner surface of the shell? I agree on the insulator in the middle. I agree the charge there is positive Q. But how much would be on the inner surface of that insulating shell, since the charges can't move?
Well,
No
wouldn't I was going to say negative because it says there's no net charge on the insulating shell. So then,
Okay.
like, since the center is positive, I don't know.
Oh, okay. I'm going to take not presenter role, but what I'm going to try to do is grab your mouse, and what I want to do is I want to draw a picture here on your picture. So here's the insulator in the middle, and I think we all agree that the charge of that is Q. It's positive Q. I agree. If there is another shell around it, so there's this other shell around the thing, and let me draw another circle here. If this were a conductor, you're absolutely right that the charges could move. So there's a positive Q here, and so the negative Qs would move near it. But are the charges able to move? In this case, because it's not a conductor, right? It's an insulator.
So no, they can't move. So then
They can't move, right? It has to be zero, right? It has to be zero. So I'm going to erase a little bit here, and then I'm going to give the mouse back to you guys, and you put in the right answer in the mouse control. You guys go ahead and put the answer in then for A. 0, right? And then what would be on the outer surface? You guys also said
0, but then
0.
that would be changed to negative.
No, wait a second. Can the charges move on the insulator?
No.
We're still sorry. We're talking about the insulator.
Yeah, we're talking about the outer shell insulator. That's 0. Okay, then finally, we want to know what is the E field inside of the the sphere in the very middle. And I see that you have Gauss's law, okay, and you've got E equals 4 pi r squared, and then I see that equals W over epsilon naught. Can you tell me
that
what
should be a Q.
Yeah.
Oh, okay, Q over
That
epsilon
was
naught.
a typo.
Okay, I got you. So my question to you is this: if I'm going to draw again for a second on yours. Okay, now let's say I draw in. Let's say I draw in a Gaussian surface. So I'm going to draw in a Gaussian surface here. I'm not doing a very good job. So imagine that I've drawn in a Gaussian surface. Is all that positive Q actually inside my Gaussian surface?
No.
No, it's not. So this equation isn't exactly right that you have there, because you're going to have to multiply Q by some proportionality of the volume.
Okay, so it is.
Yeah, so I think we're going to have to change that a little bit. So actually, let me kind of click on that a little bit, if it lets me do it. Okay, so you're going to have the E field is equal to everything that you have there. So Q divided by 4 pi epsilon naught, and I'm not sure how you guys got that E in there, and that's totally cool, times epsilon naught times r squared. But then we have to multiply some by a proportionality. So my question to you is, what will be that proportionality?
It'd be the same thing, but with big R, or like a different R, right?
Well, it's the proportionality of what? It's not the radiuses, it's the proportionality of the
Volumes.
volumes, right? So it's going to be 4 times, I'm not sure, it's not coming up here. Wait a second. 4 times, why is it not working for me? I think it's probably because I'm trying to share. I'm going to have to take back presenter role. Okay, so let me go ahead and do it on here. Or actually, is there somebody else who can share theirs with us? Maybe that'll be quicker instead of me doing it. I want to get, I don't think it'll be exactly the same because it's linear. Is there anybody who thinks they have the answer and we can have them present to make it go? Okay, Ben did. Okay, that'll make it go a lot faster. Let me pass it over, and then anybody in his group can talk.
Oh, I was just kind of asking them if that was a good idea, if we should go. But, all right.
Okay, so this is Ben's group, Ben, Mary, and Kaylin, and you guys both have 0 and 0 for A and B, and then for part C, what did you guys get for an answer here then? Ah, yeah, there it is. So at the very bottom, notice this is actually, just like on the graph on the previous group, you guys actually had the graph right. It's a direct relationship, and now you can see why there's this R in the numerator. Any questions over there? We're looking at the one in red. Any questions from the whole class? Okay, thank you very much. I'm going to take the presenter role back again. Okay, now this time what I want you to do is I want you to do it for, you don't have to do it now, but what I'd like you to do it for is 2R is greater than little r, which is greater than big R. So you're doing just part C now. We've already answered part A and B. They're done. A and B are done. And you're just answering part C, and you're looking at actually the region in between the shell and the sphere. Okay, so I'm going to give you about 5 minutes to do this, and I'm going to mute you again. Okay, we're going to go ahead and call it, and I'm going to pass off to Trevor's group, and I'm going to hand it off to Trevor, but anybody in his group can talk. Okay, so again, they have the same answers, A and B, 0. And what did you guys say for this one? You said the closed integral E dot dA equals QX over epsilon naught. So in other words, the electric flux is equal to electric flux. There's two ways to find the electric flux. Closed integral E dot dA and Q over epsilon naught. And then you guys solved it, and you got Q over 4 pi epsilon naught R squared. Any questions on that? Okay, very good. I'm going to go ahead and take the presenter role back. Thank you very much, Trevor's group. Okay, then for this next part, hoping you guys can hear me. This next part, what I'd like you to do is I'm going to need to do a little erasing. Between, that's not good. Between 3R and 2R is where I want you to solve it for. Okay, so let me go ahead and draw that in here. So 3R is greater than little r, which is then in turn bigger than 2R. Okay, so I'm going to go ahead and mute you and let you go ahead and get working. Okay, I'm going to call you back, and I'm going to pass it over to Eric's group. And again, anybody in Eric's group can present or can talk this through. Okay, and so for this one, again, for A and B, of course, it's 0. For this part, we're looking between 3R and 2R. And the idea here was that the charge enclosed, okay, the charge enclosed, you guys are saying 0. And why is it that you're feeling that the charge enclosed is 0?
Because there was no net charge on the insulating sphere outside of it.
Ah, okay. So do you guys mind if I draw on yours a little bit? I'm not sure how I do that. Let me see if I can figure that out. Let's see. Oh, over here, draw. Okay. I bet this is not gonna be very good. I'm gonna try to draw anyway. So here is the inner spherical charge, and out here is the shell. It's not as bad as I thought. And then we're looking at drawing a Gaussian in here. And you guys are absolutely right. There's no net charge on that outer insulator. And so the amount of charge it encloses in the insulating part, let me see if I could sketch that a little bit. That's this part right here. The amount that it encloses in here is totally 0. But my question to your group is there any other charge that it might be enclosing?
There's the charge of the inner sphere, but didn't we already account for that in our equations before? That now?
Oh, that was only on the previous questions. Those are kind of like all separate ones. So we still have to look at all the charge inside, not just the insulating part, but everything inside of the Gaussian surface.
Okay.
So there's still going to be a Q. So I guess my question is, how will the answer here compare to the last answer then?
It should be the same then.
Exactly the same. Yeah, and if you guys remember, I'm going to go ahead and try to write it here. We found that the E field was, oh geez, what's that? That's supposed to be an E. The E field is equal to the Q enclosed. Oh, what's it doing? I can't draw on this. How do you guys draw on this? This is driving me crazy. That's supposed to be a Q. Oh, okay. That's supposed to be a Q there. Over 4. Oh, wow. Okay, I give up. The answer is going to be the same as the last one. Okay, so let me, I'm going to take presenter role back, and I'm going to see if I can put it on my screen here. And so for this one, what we got was the E field is going to be equal to the charge enclosed, which is Q, divided by basically the area times the epsilon naught. So it's going to be 4 times pi times epsilon naught. I'm going to use, well, I don't know. I'll just go epsilon naught times r squared. Any questions on that one? Okay, then the last one here I want everybody to do is we're looking at little r is going to be bigger than 3r now. So now it's going to be this. Is it slightly easier to draw on an iPad? That's what I was kind of wondering. Okay, so I'm going to give you guys about, I think this one should be easier. I'm going to give you about 2 minutes to do this one. Okay, I'm going to go ahead and pass it to St. June's group. Let me see if I can, oh, there he is. And anybody in St. June's group can go ahead and present. I'm just passing it to St. June.
I think you should screen someone else.
Okay, so somebody, you're saying not your group or somebody else in your group?
Someone else in my group.
Okay, how about, let's see, Jacob, can I go? See.
I can't take it because the firewall online won't let me take over.
Gotcha. Let me see if I can pass it to Michael, and then anybody can talk. Doesn't have to be Michael. Okay, so now we're able to see Michael's screen, but anybody can talk.
We had a little more, but then it all got erased, so this is what I drew last minute.
Okay.
Basically, we set up the epsilon, or the E times dA equals Q enclosed over epsilon naught, and then F equals Q enclosed over 4 pi r squared epsilon naught.
And really, that's not F, right? That's really E equals all that?
Oh, yeah, I don't know why it says E on my screen.
Oh, okay.
I don't know why it says F.
Okay, so this answer really is the same as the last two answers, isn't it? Yeah. Okay, I'm gonna go ahead and take presenter role back. Thank you very much, guys. Let's see, here we go. All right. So I want to really quickly kind of look like then. Let's see if I can erase some stuff here. In other words, what I'm going to do is I'm graphing the E field versus R. So this is going to be little r here. And this is going to be the E field. And there's some important points here. There's big R. There's another important point, and that's 2R, 2 big R, I should say. And then there's another important point, and that's 3R, 3 big R. And I want to look at what the graph would look like for this. Well, if you remember for the first part, what we found was that was a direct relationship. So it kind of goes up like this. And then for the rest of the problem, it was all the same answer, and that was an inverse square relationship. And so it kind of, oops, that's not right. It kind of goes down like this. Hey, that's not bad. That's pretty good. Any questions? Okay, I only have about 5 more minutes. So what I thought we would do is maybe another problem. Let me see if I can pull one up here. So now you'll do your lab response. It basically should be all done now. But I also, I sent an email, an assignment. I kind of wanted to get started on it. We're going to whiteboard this. This is not an assignment to do by yourself. So you can attempt it. I think that would be great practice. I would like to board this class, and we'll maybe get started on this one. We probably won't finish it. Do you guys have questions for me? I see you're typing some stuff. I'm not sure if you guys are, bless you. I'm not sure if you're wanting me to answer something. If I miss something, please let me know. Okay, so I emailed to you a worksheet that we're going to be whiteboarding. And let me just present the first problem here. The first problem is you have 2 thin concentric spherical shells of radius R1 and R2, kind of like in the picture there. And they contain a uniform surface charge density, and it's sigma 1 and sigma 2. And you can kind of see it in the picture. Determine the electric field for R is less than R1. So inside here, imagine drawing a Gaussian surface. Part B, for R is greater than R1 but less than R2. So imagine another Gaussian surface out here. And then finally for part C, draw another Gaussian all the way out here, trying to figure out what the E field is. And then in number 2, we're going to take your answers there. You're going to either see, no relationship, you're going to see inverse, inverse square, direct relationship, something. We're going to kind of sketch what that would look like. So any questions? We're not going to get all this done because we only have 6 minutes.
Are these shells conductors or insulators? One of each, or?
You know what? It doesn't say, but what it does say is it says neglect the thickness of the shell. So in other words, we can pretend they have 0 thickness and it's just a bunch of charge smeared out here in space. Does that make sense?
It doesn't matter if they're insulators or conductors?
Yeah, because it doesn't matter because they can't really move. The charges can't move. It's
okay.
Exactly, yeah.
So it's like we're treating them like they're insulators because the charges can't move?
Right, but they have 0 thickness as well, right?
Okay.
Yeah.
Okay.
So let me give you about 2 or 3 minutes just to do the first part here from 0 to R1. So you're drawing, let's see if I can kind of draw it in here. You're drawing a Gaussian surface in here. And I want you to figure out the E field inside of there. Okay, so let me mute it and give you guys a little bit of time to do that. Okay, I'm going to ask, I think, Jack's group to present, and I'm not sure if you guys need me to switch the presentation role to you guys, or can you just tell us verbally what the answer is? Do you need it? You need me to switch to your screen? Can you guys hear me?
I can.
Can anybody? Oh, okay. Yeah, I can. Okay, can Alex, Jack, or Matt hear me? Anybody in that group? Jack can. Okay, so I'm going to switch it to Jack's screen because we're not hearing him. So maybe he. Okay, Jack's mic isn't working, but I can switch it to him, and maybe we can see his answer on his screen. So, so what's the answer there? It looks like we just said it was linear. Okay, so you're saying it's linear. Okay. Let me go ahead and take the presentation role back for a second. Okay. Okay. It would be linear if there was in here. But let me just ask the group right now. We're running out of time, and I want to let you go in like a minute or so. How much charge is enclosed in this?
Zero.
There's zero charge enclosed. So how much electric field would be inside there?
Zero.
Zero, right? Yeah, so the answer here, you don't really have to do a whole lot of work because the Q enclosed is zero, which means the flux through there would be zero, which means that the E field through it is zero. So therefore, if you're going to be making a graph, it would kind of look like this all the way up to R1. Yeah, Nick, it is zero. Okay, so that's what the graph would look like. Okay, I want to let you guys go then, but before I let you go, does anybody have any questions on that right there?
Nope.
No questions? Okay, so you can try some of these problems. In fact, I would encourage you to try some of them. That way when we start whiteboarding, maybe it'll go a little bit faster. Okay, so thanks. I'm sorry, go ahead.
Will we be whiteboarding these tomorrow, whether we're in class or on here?
Yep.
Okay. Cool.
Any other questions? Okay, now everybody knows that the next time we're together, this lab that we just whiteboarded, that's due, right? No questions on that? Okay, thanks. I'm going to go ahead and stop the recording and see you guys later. Bye.